setting the AI-BAC machine for Calcutta, India. 1924. Today we meet Satyendra Nath Bose, the brilliant physicist whose revolutionary approach to counting particles of light changed our understanding of the quantum world forever. His work laid the foundation for technologies we use every day, from lasers to quantum computers.
In my laboratory at Calcutta University, I discovered something quite extraordinary about light itself. You see, when we count particles of light, photons, they do not behave as Newton would expect. They are not like marbles in a box, no. Multiple photons can occupy the same quantum state, defying our classical intuitions. This changes everything, from how stars shine to how atoms behave at the coldest temperatures imaginable. What I found was not just a new way of counting, but a new way the universe works, isn't it? Einstein called it beautiful. I call it simply what is. Sometimes the most profound truths hide in the mathematics we think we already understand. Let me show you what I mean. Here is my counting formula. W equals n factorial, divided by the product of ni factorial. You might think this looks familiar, and you would be quite right, but the revolution is in what we count. Classical physics says particles are distinguishable like numbered balls. But light particles, photons, they are truly identical. Not just similar, identical, you see. When I applied this insight to Planck's radiation law, something magical happened. By Jove, I derived the correct formula, but through a completely different path. My colleagues thought I had made an error in my counting, but the universe agreed with me. This led me to what we now call the Bose-Einstein distribution. The average number of particles in any quantum state follows this beautiful formula. Notice the denominator, e to the power of energy minus chemical potential, divided by kT minus 1. That minus 1 is crucial, you understand. It means something impossible in Newton's world becomes not just possible, but inevitable. Multiple particles sharing exactly the same quantum state. When I sent my paper to Einstein, I was quite nervous, I must say. Here was this young professor from Calcutta challenging the very foundation of statistical mechanics. But Einstein, he saw immediately what this meant. He helped me publish it and then extended my ideas to matter particles. Together, we predicted something most extraordinary. At temperatures near absolute zero, atoms would suddenly collapse into a single quantum state, behaving as one giant superatom. It took 70 years for technology to catch up and prove us right. By George! They called it a Bose-Einstein condensate. The partition function, this elegant mathematical object, captures the very essence of quantum statistics. Each term represents the infinite ways indistinguishable particles can arrange themselves. But here is what still amazes me. This mathematics that seemed so abstract in 1924, it now powers the lasers that read your music, the superfluids that cool your quantum computers, the very tools that allow us to probe the deepest mysteries of the universe. I began with a simple question. How do we count particles of light? But what I discovered was that the universe itself thinks differently than we do. Reality is far stranger and more beautiful than our everyday experience suggests. No, nature doesn't care about our classical intuitions. She follows her own mathematics. And when we learn to speak her language, truly speak it, she reveals secrets that transform not just our understanding, but our entire world. These symbols on the board, they are not just mathematics. They are nature's own handwriting, telling us how she thinks about identity, about sameness, about the fundamental question of what it means for two things to be truly identical. And that, my friends, changes everything.